Okay, so now we move on to the derivatives of trig functions. I'm going to discuss I'm going to discuss the definition of these functions and a few identities first, and then we will calculate their derivatives. Okay, so first, let's define the trig functions. So I'm showing you the unit circle here of radius 1 centered at the origin of the xy plane. And if you draw a line out from the center of the unit circle at the origin at an angle of alpha radians from the positive x-axis, and then you hit a point on the circle xy, and at x, the x value is the cosine of alpha, and the y value is the sine of alpha. So that's one way of defining the cosine and the sine functions. Okay, so on the unit circle x, if t is in radians, then there's a point xy on the unit circle, which is given by drawing a line that makes a angle t radians with the positive x-axis, and then that point will be x is equal to cos of t, y is equal to sine of t. We define the tangent as y over x, or cosine over the sine, provided that the x value is not 0. And then, because you're on the unit circle, x squared plus y squared is equal to 1, which means that cos squared t plus sine squared t is equal to 1. Okay, so the way we have defined these functions right now, if f of x is equal to sine of x, mapping from reals to reals, it's not 1 to 1, it's not onto, and it does not have an inverse. We'll get to what the inverse sign is later, but right now it doesn't have an inverse. Similarly for the cosine function. Okay, here's a couple of identities that can be used when you're deriving limits. They're useful. So the cosine of a plus or minus b is cos a cos b minus or plus the sine of a times the sine of b. And the sine of a plus or minus b is equal to sine of a cos of b plus or minus cos of a sine of b. Okay, and a couple of useful limits. As we've already seen, the limit as h goes to 0, sine of h over h is equal to 1. And we will also make use of limit as h goes to 0 of cos of h minus 1 over h is equal to 0. So now we proceed with the derivatives of the sine and the cosine function. So let's say that f of x is equal to sine of x, then f of x plus h is equal to sine of x plus h, and now we make use of the identity. That's equal to sine of x cos of h plus cos of x sine of h. Now we calculate the difference. So it's sine of x cos of h plus cos of x sine of h minus sine of x. Notice that we have here the first term has sine of x being multiplied by cos of h, and the last term has a sine of x being multiplied by minus 1. So let's pull out the common factor of sine of x, and we can write the difference, f of x plus h minus f of x, as sine of x times cos of h minus 1 plus cos of x sine of h. And now that we have the difference, we can divide by h to give us the difference quotient. So the difference quotient is sine of x cos of h minus 1 over h plus cos of h sine of h over h. You'll recognize that in the limit as h goes to 0, which we need in order to take the derivative, cos of h minus 1 over h will go to 0, and sine of h over h will go to 1. Okay, so how do we calculate the derivative of the sine of x? We take the limit as h goes to 0 of the difference quotient. So the limit as h goes to 0 of sine of x times cos of h minus 1 over h plus cos of x sine of h over h. Now, sine of x is some real number. It's a constant. It's h which is changing in this case. So we can pull the sine of x outside and the cos of x outside, and the limit of the sum is the sum of the limits. So we can do the limits individually. And so that first limit goes to 0, that second limit goes to 1, and you get that you have sine of x times 0 plus cos of x times 1, which leaves you with cos of x. Okay, so the rule is that the derivative of the sine of x is equal to cos of x. As an example, d by dx sine of kx equals k cos kx, right? You have an outer function which is a sine, and you have an inner function which is kx. This is a composition of those two functions, so you use the chain rule. So you would have cos of kx is the outer derivative, and then the inner derivative of kx is k, so we get k times cos of kx. Okay. Now, as an exercise, you should go and review the derivation of the derivative of the sine of x, and in much the same way, you should be able to show that the derivative with respect to x of cos of x is equal to minus sine of x. So, for example, the derivative with respect to x of cos of kx will be minus sine of kx times the inner derivative, which is k. So you will get that the derivative with respect to x of cos of kx is equal to minus k sine of kx. Okay, let's take two derivatives of a cos of kx. d2 by dx squared means take the derivative and then take the derivative again. So if y is a cos of kx, then d2 by dx squared y of x is d2 by dx squared a cos of kx. That's the derivative taken twice of a cos of kx. So that's the derivative of a is a constant. Don't have to do anything with that. The derivative of cos of kx was minus k sine of kx. So now we have the derivative with respect to x of minus ka sine of kx. Let's pull the minus ka, which is a constant, outside of the derivative. So that's minus ka times the derivative of sine of kx, which is minus ka times, as we saw before, k cos kx, which is minus k squared a cos kx. But a cos kx was the original function, so this is minus k squared y of x. So in the case where the function y is of the form a cos of kx, we see that y double prime plus k squared y is equal to 0. You might recognize that as the equation for simple harmonic motion if you have taken a mechanics course. Okay, second, taking two derivatives of b sine of kx. I leave that to you to follow the same sort of algebra as we did in the previous example. So if you have y of x is equal to b sine of kx, and you take the derivative twice of y, you're going to get minus k squared y of x. And then you move the minus k squared over to the other side, you'll get second derivative of y plus k squared y is equal to 0. Now, if you let y of x equal a cos of kx plus b sine of kx, now once again, if you go through the steps, you will see that y double prime of x plus k squared y of x is equal to 0. So if I were to suggest to you that there's a function y such that y double prime plus k squared y is equal to 0, then one solution of that will be a cos of kx plus b sine of kx, where a and b are arbitrary real constants. Okay. Now we look at the linearization of sine. This is something that's used a lot in physics, for example. In the if you've done a first physics course, then in the simple pendulum experiment, this approximation is used. Okay, so linearization at x is equal to 0. So how do we do this? So this is the function is approximated by this linearization at 0, which is the function at 0 plus the derivative of the function, the derivative of the sine function evaluated at 0, times x minus 0. Well, sine of 0 is 0, and the derivative of sine is cosine, and the cosine of 0 is 1. So for very small x, for x close to 0, sine of x is approximated as x. Okay, so that was the derivative of the sine functions and the cosine functions. And now we will go on to taking a look at the derivatives of other trigonometric functions, making use of the rules that we've had before.